Okay, problem 5.66 says air discharges from a 2-inch diameter nozzle and strikes a curved vein, which is in a vertical plane as shown in the figure. A stagnation tube connected to a water U-tube manometer is located in the free air jet. Determine the horizontal component of the force that the air jet exerts on the vein. Neglect the weight of the air and all friction. Okay. So we're trying to find the force that the water is going to exert on the vein, and to do that we are going to need to do a analysis, a control volume analysis on the linear momentum of the system. So let's highlight a control volume, and we're going to have flow coming in, and we're going to have our control volume be our fluid of water, of air, excuse me. Okay. So we're going to have some momentum crossing our boundary at position 1. Okay, we'll call this position 1, the inflow. And then we're going to have some momentum leaving, crossing the boundary at position 2. All right. So in addition to that, we're also going to have some force that the vane places on our control volume. This is an external force placed on our control volume. That's going to be the reaction force, call it R sub x, and that's the force that the vane is going to exert on our fluid. So let's take a look at our momentum equation. Let's look at the x momentum. Okay, let's start to. And when we do that, for a steady state, we know that it's equal to the sum over, or the integral over the control surface of u times rho times v dotted with n times dA has to equal the sum of the forces in the x direction. And we can rewrite that with our forces. The only force in this problem is that horizontal reaction force. There's no, we're told to neglect weight and friction, and we and we also know that the exit of our free jet is 0 gauge pressure, and also at position 2 it's also open to the atmosphere, so it will also be 0 gauge pressure. So there's going to be no pressure force either. So the only force we have is that reaction force that's pointed in the negative direction, so I'm going to have a minus R sub x. Okay. This integral, our velocity vector is always perpendicular to our exit area. Therefore, that integral is going to simplify, and will just be the momentum coming in is negative, so we have a minus, and the flow coming in, this will be u1 here. So we'll have u1 times the mass flow rate, and then leaving a control volume is positive. So position 2 we have momentum leaving, so that's plus, that will be u2 times m dot. That's equal to minus rx. Okay? Okay, so we should note a couple of things. So let's note that our velocity at 1, the entire velocity is purely in the horizontal direction, or the x direction. So I can say that u1 is just going to equal v. Okay. Now, I also know that the area of that jet isn't changing. So between position 1 and position 2, continuity tells us that v1 times a1 equals v2 times a2. if I'm assuming that as the flow turns, it's not increasing in area, that means A1 equals A2. So I'm going to assume A1 equals A2. Therefore, V1 must equal V2, and we could just write V. Okay? So you back to our notes here. So U1 is equal to V, and then U2 is just equal to minus V cosine of theta, right? So I have this velocity vector, and I only want the horizontal component, so I just want this guy. So that is going to be V cosine of theta. It's pointing in the negative direction, and that's why I have my minus sign. So U2 is a negative V cosine of theta. All right. So what other information do I have? Well, I don't know what V is yet. But I do know that I have a stagnation tube in my flow stream, and that is hooked up to a manometer. Now, the stagnation tube, so this pressure right here, where I've just drawn this arrow, is going to be measure the stagnation pressure, which is the static pressure plus the dynamic, 1/2 rho V squared. Okay? The other end of my manometer is going to have a pressure that's open to the atmosphere. So this is just going to be P static or P atmosphere. Okay? So if I look now, the only difference between the pressure from one end to the other is going to be the dynamic pressure, 1/2 rho V squared. Okay? Because my static pressure from the stagnation tube is the exit of a free jet, so I know that my static pressure is the atmospheric pressure. The other end is open to the atmosphere, so that's also atmospheric pressure. So the only difference in pressure is going to be due to the 1/2 rho V squared. Okay? So then for my manometer analysis, I know that that 1/2 rho V squared has to equal the pressure difference measured by the manometer. And this pressure difference is just rho of water, the density of the manometer fluid, times G times its height, the height difference, H. Okay? So this will give me 1/2 times rho of air, the density, be specific, this is the rho of air. That's the density of air because our flow is air, so that has the dynamic pressure, right? So it's 1/2 rho of air times V squared. And that is equal to the pressure developed by that manometer. The manometer fluid is water, so that has the water density. Okay, so we have 1/2 rho of water is 2.38 times 10 to the minus third, okay, times V squared. And that has to equal rho of water times G, which is the specific weight. And for water, we know that's 62.4. And times H is 7 inches. So I'll put 7 divided by 12 to put it in feet. Okay? One equation, one unknown. I can solve for the velocity. And the velocity of my airstream is then 174.9 feet per second. Okay, so now I've solved for V, so that's good because I need that for my momentum equation. Okay, so we'll go ahead and rewrite our momentum equation that we had before. We had minus U1 times m dot plus U2 times m dot has to equal minus r sub x. We can pull out the m dot, and we'd have m dot times U1 we said was equal to V plus U2 we said was minus V cosine of that theta, or that was 30 degrees, okay, equals minus r times x. So I see I also have a V that is in both of my terms. I could pull that out. So I will have V times m dot times minus 1 minus the cosine of 30 degrees equals minus rx. Plug in my values. I have, oh, we still need to solve for m dot. I'll do that quickly. So note, m dot is equal to rho times v times a. So the rho of air, 2.38 times 10 to the minus third, times the velocity we solved for above. That was 174.9. And then times the area. At location 1, it's pi over 4 times, it was 4 inches squared. So 4 over 12. I'm sorry, it was a 2-inch diameter. 2 over 12 squared. And you find that the m dot is equal to 0.00908 kilograms per second. Right? So let's go back and plug into our momentum equation. The velocity was 174.9. The mass flow rate, 0.00908. That's times by a minus 1 minus cosine of 30 degrees equals minus r times r sub x. One equation, one unknown, and I would get that rx is equal to 2.96 pounds. Okay? Now this is the force that the vane exerts on the airstream. The problem asked us for the force the air puts on the vane. So the force the air puts on the vane is going to be equal in magnitude but opposite in direction. Force air puts on vane is therefore 2.96 pounds to the right.